Chris, could you introduce yourself?
Hi, I'm Chris Rackauckas, applied math instructor at MIT, senior research analyst at the University of Maryland School of Pharmacy, and a director of scientific research at Pumas AI.
And what are you doing with Julia right now?
So what I do with Julia is I build the scientific machine learning ecosystem. So this is the SciML ecosystem, sciml.ai. And what we do is we do machine learning mixed with scientific models. So how do you make scientific models fast, and how do you represent them in such a way that you can automatically discover physical equations? So I work on a lot of the differential equation solvers and a lot of these tools that underlie, the climate modeling tools and the quantum mechanics simulators and all these portions.
And what problems might I use to apply these differential equations, techniques, and machine learning in the real world?
Yeah, so a lot of what I'm using it for is for personalized medicine. So how do you do things like understand how I will react to a drug differently from you? These covariates like age, height, sex, and weight, they can cause differences in metabolism. And what we want to do is we want to understand how we should be dosing individuals differently, or how we should be checking them differently, how they should be going to the clinic at different intervals, right? All these things we can understand by understanding the underlying models for how the drug dynamics in our body are different. Another case that we're also looking at is, in quantitative systems pharmacology, you have this problem where someone can suggest that a drug should target protein X, but protein X does 10,000 things in your body. Can you predict what the actual side effects of the targeting protein X is before you send it through a $3 billion clinical trial? And so all these kinds of things are all these kind of scientific questions that require understanding and simulating, living systems, or even physical systems like climate models and quantum mechanics systems, or battery-powered airplanes. All these kinds of things are using our differential equation solvers.
So you blog a lot about how Julia is a great language for solving these problems. What's one feature that makes Julia a perfect language for this kind of problem solving?
Yeah, so the thing that really makes Julia great is its multiple dispatch, right? You can't talk about it enough. Essentially, what multiple dispatch allows Julia to do is, at the surface, it means that Julia is fast because of multiple dispatch, right? It's not just a language feature, but because every single function call is allowed to specialize on its arguments, that means that the compiler itself is able to build a fast version for every single function you're calling, right? That's why Julia is fast. But at the same time, it means that you can write one function in its generic form and have it be optimized for all forms. The way I really like to explain why that matters is because if I say the equation 2x plus y to you, you know what I mean. But as a mathematician, I'm like, haha, I just tricked you because 2x plus y doesn't mean anything. I didn't tell you if x and y are integers. I didn't tell you whether x and y are real numbers, right? In every single one of those contexts, they actually have a slightly different meaning, right? And what you can do in Julia is you can say, my function is 2x plus y, and every single time someone changes the input types, it'll create the optimized version for those input types. So the differential equation solvers are written in their mathematical form. But every single time that someone does something like, oh, I want to use arbitrary precision arithmetic, it generates a new version of the ODE solvers automatically that is optimized for arbitrary precision. If someone wants to use low precision arithmetic to really get the most speed out of it, it just generates a version automatically. If someone wants to add error bars to it, you can define a number type with error bars, and it generates that automatically. That one we actually found out works because someone told us on the discourse forums that they put a number with error bars into our thing, and it got appropriate error bars out. So, like when the thing that you get from your code is that it generates so much code that you don't even know the number of features, and they're all optimized, that's a pretty good feature. So.